All right, so lastly, we're going to talk about acid-base titrations. Titrations are an important laboratory technique. Let's talk a little bit about those. So first of all, how these kind of experiments go down is we're going to do what's called a titration again. And what that means is that we have this solution of base where we precisely know its concentration. Okay. And we're going to add that gradually to a solution of acid that doesn't have a known concentration, right? So what we're going to be able to do is, since we know the precise volume and the concentration of the base we're necessary to neutralize the acid, then we can calculate the amount of acid neutralized. All right, so these are all about, one of these components, the base concentration and volume. You're going to use it to find the acid concentration and volume. I think actually just like pictorially looking at this might make a little bit more sense. These are what we have when we have a titration. This thing here, and actually the rest of it should have been pictured, is this big cylinder called a burette. And this burette has markings on it. So, 15 milliliters, 16 milliliters, 17 milliliters, et cetera, et cetera. You fill this burette with one of your solutions. In this example, it's the base, right? So within my burette, I have a whole bunch of hydroxide ions. And then we're going to add that to a flask that contains acid. So in this case, so here's my base. I'm adding that to this flask that contains acid, right? So if we just do an example reaction, sodium hydroxide plus, oh my gosh, why am I blanking? Hydrochloric acid, holy cow. What's going to happen as I slowly add in my base? Well, it's going to react with that hydrochloric acid to form water and sodium chloride. So each drop of base that I'm adding is going to be converted into these products, right? So that's going to happen as I continuously add base. I'm continuously adding that base drop by drop in that burette, right? This thing here is like this little open and close valve where I can slowly add stuff and then turn it off if it's, once I've added enough, etc. So like halfway through your titration, you're going to have most of your acids converted to water, but there's still some hydronium ion concentrations. So I'm going to continue to add until I get to what's called the equivalence point. This means this is the exact point in which all of that acid has been neutralized. So after my titration is over, and then I'm going to stop, right? So now all acid and base has reacted. And you see that the solution looks like a little pink. So basically we have this compound in there. It's like a pH indicator that will change colors to pink once that reaction has been complete. Once all of the acid has been used up, the solution turns pink and you know to stop. All right. And then since our burette has these volume readings on it, we know exactly how much base we added. We know the concentration of the base. We'd have to know that beforehand. So we can use that to calculate what the concentration of our unknown acid is. This is an acid-base titration. All right, so in order to do the math behind these behind these titrations, basically they're always stoichiometry. All right, so these are just stoichiometry problems. What do we need before we can do any sort of a stoichiometry problem? A balanced chemical equation. So step one is to get a balanced chemical equation. So let's look. It says we have 25 milliliters of hydrochloric acid, and it requires 46.3 milliliters of 0.203 molar sodium hydroxide to neutralize. What is the concentration of HCl? So I know the volume of HCl that I start with, but I don't know the number of moles. I don't know the concentration. So my goal is to find moles HCl, and then I can divide that by the volume HCl, right? This would give me molarity HCl. Again, before I can do that, I need a balanced chemical equation. HCl plus NaOH gives me H2O and NaCl. Now you're going to start with what you know, which is the concentration of base and the volume of base that you added. So 46.3 milliliters of the NaOH. Again, I'm going to be really good with my units and always not only say like the volume, but who I'm talking about. I want to use that concentration, but it's in molarity. Remember, this is moles per liter. So actually the first thing I have to do is make that jump from milliliters to liters. Now I can use my concentration, which is 0.203 moles of NaOH in 1 liter. And I'm trying to get to moles of hydrochloric acid. So then I'm going to use my balanced chemical equation, which tells me that 1 mole of NaOH is consumed along with 1 mole of HCl. Okay, so I punched that into my calculator and I would get 0.00939989. Going in back and paying attention to units. Milliliters will cancel out, liters cancel. Finally, moles of sodium hydroxide cancel out. So I'm left with moles of HCl. Got to pay attention to sig figs. I have 3 sig figs in my volume and 3 sig figs in my concentration. So I should have 3 over here. But I'm not going to round it off yet because what the problem actually asks for is the concentration of HCl solution. So now I have to take the fact that I know that it was 25 milliliters that I started out with. So I'm going to take the concentration of HCl is going to be equal to my 0.00939989 with my sig fig marked, moles of HCl, divided by 25 milliliters, which I am going to have to convert to volume or to liters. So this would be equivalent to 0.0250 liters. You could, if you can't do it in your head, then you would want to use this conversion factor here. This is what I did, and I plugged that in, right? So that's how many how many liters I have. Punch that in to your calculator, and you would find that it's 0.3759. And moles divided by liters, nothing cancels out here. Instead, I'm left with molarity, which is moles per liter, right? So I'm just going to combine those into big M. And lastly, I need to pay attention to sig figs. I should have 3 sig figs. So 0.376 molar HCl. That's my unknown acid concentration. Okay. So again, just to take a step back to what exactly we did in this problem, we knew the volume and concentration of the sodium hydroxide. So that was this one here. And we used that to find the unknown concentration of acid, right? So we knew one of those species. We used it to find the concentration of the other species. Okay, I'm gonna have to make some room here to answer the second problem here. Okay, if 25 milliliters of H2SO4 solution requires 46.3 milliliters of 0.203 molar NaOH solution to neutralize, what's the concentration of sulfuric acid? So here again, similarly, my goal is to find moles of sulfuric acid so I can divide it by the volume of sulfuric acid to get the concentration or the molarity of that sulfuric acid. Again, because this is stoichiometry, what am I going to need first? A balanced chemical equation. Here we have NaOH, But since sulfuric acid is a diprotic acid, this is going to form water and sodium sulfate. You're going to note that to balance it, I'm going to need to use 2 moles of sodium hydroxide per mole of sulfuric acid, right? Because there's 2 protons on this acid. Otherwise, it's set up the same sort of way. I'm going to use my 46.3 milliliters NaOH. First, I got to convert it from milliliters to liters, and then I can use that concentration of NaOH, 0.203 moles NaOH. If I stopped here, this would give me moles NaOH, but of course I want to find the moles sulfuric acid. That's my goal. So now I'm going to jump from moles NaOH to moles sulfuric acid by using the fact that 2 moles of NaOH are consumed along with 1 mole of H2SO4 in this reaction. So punch that into my calculator, 0.00469. Go back paying attention to moles, or sorry, paying attention to units. Milliliters will cancel out, liters cancel out, moles of NaOH cancel out, and I'm left with moles H2SO4, which is what I want. But the ultimate goal here is to figure out the concentration of H2SO4. So I'm going to take that 0.0469995 moles H2SO4 and divide it by that initial volume, which is 0.250 liters. Again, I just kind of in my head converted from milliliters to liters. All right. Actually, one thing I forgot is sig figs. We have 3 sig figs in both our volume and concentration. So that means we would round to 3 sig figs over here. I'm not actually going to do the rounding because I'm still doing calculations, but I will mark my sig fig. So then lastly, I'm going to punch this into my calculator. It's going to spit out 0.118797. Paying attention to units, again, nothing cancels, but I can combine this moles per liter into big M molarity. And then lastly, sig figs, I should have 3 sig figs in my answer. So the concentration of H2SO4 is 0.188. It's really messy. Molar. Okay.